Here I'm comparing how two identical ice cubes melt under different conditions. The one on the left is sitting in room temperature air, and the one on the right is completely submerged in room temperature water. Even though the temperature of the surroundings is the same, these ice cubes don't melt at the same rate. This simple setup gives us a real-world look at how heat transfer works. The melting of each ice cube begins with conduction, heat flowing from the warmer surroundings into the colder ice. The basic equation that describes conductive heat transfer is Q is equal to K times A times the temperature difference divided by L. In this equation, K is the thermal conductivity of the medium, A is the contact surface area, delta T is the temperature difference between the ice and the surroundings, and L is the thickness of the boundary layer. What matters most here is that the value of K for water is much higher than the value of K for air. That means water delivers heat to the ice much more effectively than air does. But conduction isn't the only mechanism at work. The submerged ice cube also experiences strong convection. Convection is described by the equation Q equals H times A times the difference between the surface temperature and the surrounding temperature. Here, H is the convection heat transfer coefficient. Water has a much higher H value than air because water molecules can move past the ice cube more efficiently. As the ice cools, the nearby water, that cooler water sinks and is replaced by warmer water, creating continuous motion. This keeps bringing fresh thermal energy to the surface of the ice. In contrast, the air around the exposed ice cube doesn't move very much. Cold air tends to stagnate around the ice, creating a thin, insulating layer that slows down further heat transfer. So if we compare the two cases, the ice cube in the air relies mostly on conduction through a poorly conducting medium with almost no helpful convection. Meanwhile, the ice cube in water benefits from both strong conduction and strong convection working together. The result is much higher overall heat transfer rate in the water case, which is why that ice cube visibly disappears faster. For the ice to actually melt, it needs to absorb a certain amount of energy known as the latent heat of fusion. This is described by the phase change equation Q is equal to M times LF, where M is the mass of ice and LF is the latent heat of fusion. This energy doesn't raise the temperature of ice. Instead, it's used to break apart the molecular structure of solid ice so it can become liquid water. The key question in this experiment is, which environment delivers this required energy faster? And based on what we observe, that environment is definitely the water. This melting process also reflects fundamental laws of thermodynamics. The first law, the conservation of energy, tells us that the energy transferred from the water or air doesn't vanish. It becomes the internal energy needed to melt the ice. The second law explains why heat flows into the ice in the first place. The thermal energy naturally moves from a region of higher temperature to a region of lower temperature. As the ice melts and becomes liquid, entropy increases, which aligns perfectly with the direction favored by the second law. By watching these two ice cubes melt side by side, we can clearly see how conduction, convection, and basic thermodynamic principles determine the rate at which energy flows. Even a simple kitchen experiment like this reveals how powerful and important heat transfer mechanisms are in everyday life.